So I'm going to this is going to be a very dramatic change from the lecture you had this morning. But in its way, I think from what I've been hearing of the skills of the students, I think you might be more comfortable with what you were doing this morning than you might be with some of the engineering stuff I'm going to expect you to do this afternoon. Anyway, so there's the outline. I'm going to give a little bit of history, not too much, because Sten Odenwald has already given you a good background on that. But the main thing I want to concentrate on is to actually explain how magnetic disturbances affect power system. It's not just you get a magnetic disturbance and then everything goes, sort of falls apart. There's a very specific steps and there's very specific types of disturbances cause problems, and I hope to give you a better understanding of that. And then I also want to show you that this is not a closed subject. There's a lot of new knowledge that is needed, and this actually kicks things back a lot into your field, where we need new plasma physics knowledge about different areas in the heliosphere that are the sequence of events that cause all these problems. And then at the end, I'm going to talk a little bit about assessing geomagnetic risk to power systems, and then for the lab, after the break, we're going to get you actually doing some of that yourself. So the first part, what's happened? Well, there's a whole range of space-to-weather effects on different types of technology, all the way from satellites to ionospheric disturbances affecting radio communication and things like GPS systems. But we're going to focus on things down on the ground and specifically on the electric power systems. But just to give you a bit of context, this is not a recent phenomenon. It goes all the way back to 1847. That was the first time that geomagnetic disturbances were reported on the telegraph system. And all of the diamonds along the top are specific incidents where there were reports in the literature on technological systems. The early ones were on the telegraph system. From 1940 on, it is more effects on the electric power system. And then I'm showing pipelines here, and that's shown as a line rather than as diamonds, because there isn't a specific effect on a pipeline that you can tie to a magnetic storm. It's more the problems with the cumulative effects on the pipe of causing the corrosion of the pipe. So that's why that's shown like that. Of course, the event you've all heard about is the Carrington event of 1859. And there was lots of auroral displays then, so it was very much reported in the newspapers. But then there were lots of reports of the problems on the telegraph system. And to give you a feeling for how significant the telegraph system was at that time, it's been described as the Victorian internet. So if you can imagine what would happen if the internet went down now because of a geomagnetic storm, everybody would know about it. Well, this was the telegraph system was the main means for long distance communication, and so when there were problems on this was very widely reported. And these, I'll let you read the quotes yourself. There's some lovely descriptions of the problems that occurred, and this is from one in Washington. And as well as being very descriptive, a lot of these accounts actually recorded the times when they had problems. These ones over here, so here they've got, in terms of local time, but it was useful nonetheless. And we were able to put together a record of when these problems occurred. And this was the early days of magnetic recordings using photographic instruments. This, for those of you who might have heard of this event as being classed as the largest magnetic storm ever reported, is based on these records from the observatory at Bombay, and specifically this extreme fluctuation. And people have used that to estimate what the DST would have been during that storm. It's about 3 times larger than anything else we've seen. You can see that there was actually two storms here. The flare that Carrington saw occurred on the 2nd of September, and that produced a magnetic disturbance about a day later. But there was a disturbance a couple of days before that, and we've estimated, based on this, expecting that it's the same active region on the sun that caused the problems, where and when an eruption must have taken place on the sun to have caused this disturbance. And then you can see that the times of the telegraph effects match up very nicely with the times of the magnetic activity. Okay, so I mean, that's been widely distributed that there was these problems, but the thing of interest from a physics point of view is, why do magnetic disturbances affect systems like the telegraph system? So this is a diagram that they would use Morse code, so there's the Morse key, and the operator would press down on the key, and then that would bring this battery into circuit. So come around here along the lines, and then would operate the device at the other end. And the complete circuit was completed because the operator is not pressing his key, so there's a connection through here down to ground. So you've got a complete loop through here. And so that they could send signals in either direction, when they went using the system, the spring is holding, there's a connection through there, and there's a connection through there to ground. So both ends are grounded. So whichever end the operator actuates the key, the signal goes and there's a path to ground at the other end. But what they found during the storm was that neither operator was doing anything, but they were getting the signaling apparatus was operating, and that's because of induced voltages on the lines. And so they were getting a lot of chattering of the equipment. So these effects continued. This is another big storm in 1903, where reports of problems around the whole world, and there's another one even about in Russia that it stopped the trams. Another big storm was in 1921, and the electric currents induced in the telegraph were so large that they burnt out part of the apparatus in a telegraph station in Sweden and set the whole place on fire. So this is some photos of the system after the fire, and there's all of the rest of the shell of the building is left, but the rest of everything else is burnt out. Right, to come up to the modern day, the main systems we're concerned about now are the electric power lines and also oil and gas pipelines, are the two major systems where you've got long electrical conductors stretched over the Earth's surface. And the famous event is on March the 13th, 1989. You've probably all heard about this. And this is the Hydro-Quebec electric system. And key features to point out: a lot of generation on the rivers flowing into James Bay. This is on the bottom of Hudson Bay up here, or on the rivers at Churchill Falls here. And then very long power lines bringing the power down to the load centers in the south, to the Montreal area. There's also a DC line coming down from here, that dash line that goes all the way down here and then feeds electric power into the US. On this day, an Aurora electrojet that's normally sat higher up across Hudson Bay moved down right across the top of the system, and that induced electric currents that flowed across the network. They caused problems with the transformers, and I'll explain this in more detail in a minute, caused various devices to trip out that were maintaining stability of the network. So a sequence of things tripped out there. That then caused the lines to trip out because the system was starting to go unstable. And then finally, you'll notice that with these three lines tripped out, all of the generation up here is disconnected from the load down here, and so there was a voltage surge at the north end that caused damage on the transformers, and then finally everything shut down and there was a complete blackout of the whole system. And so the people of Quebec woke up the next morning with no power, and they're having to make a coffee by a candlelight, as in this picture. There's one anecdote I must tell you on this. Hydro-Quebec had a very bad reputation at this time. There have been sort of lots of little blackouts because of poor maintenance and things. So this kind of really reflects the attitude then. And so when Hydro-Quebec announced, well, sort of, don't blame us, it's a magnetic storm, it's a sort of thing from the sun, and the general media response was, these guys have got to be desperate. No one's going to believe a lame story like that. So they phoned up our lab, and I wasn't working there then. I got recruited in the wake of this storm. But the fellow who was head of the lab then tells the story that he got these reporters phoning up, and they said, well, we've heard this ridiculous story about magnetic storms affecting Hydro-Quebec, but we feel we should just check with you. And he said, well, he started to explain, well, yes, magnetic storms can affect power systems, and yesterday we had the largest magnetic storm we've ever seen. And he says, you could just hear the enthusiasm drain out of the reporter's voice. Instead of a nice, juicy, kick Hydro-Quebec story, it's one of those science stories they're never very comfortable with because they don't quite understand. We went back a few years ago and got all these newspaper records because we were asked to look at, well, what was the economic impact of this? And we found a very interesting article here that describes all of the systems that were shut down. So all of the car plants were shut down. There was an aluminium smelter was shut down. And it's not just a matter of just switching it back on afterwards. All of the aluminium that is solidified in the vessels had to be chipped out before they could restart that. Milk processing plants were shut down. The newspapers themselves, sorry, we've got a little bit up here saying sorry for the delay of the papers. Their printing was shut down on the 13th. But in this article over here, they've got a very disturbing line about the breweries having to shut down. But the next sentence is much more reassuring because they say that the lost production will be made up through overtime. There was other problems during that storm. There were some transformers that burnt out in the US. And I show you this picture, and it's worth giving you a sense for the scale of these things. I need to get back myself. This there's a curious history to this photo. There was a picture. There was a person standing in this photo in the original picture, and for some reason they decided to fix the photo to take that person out. I don't quite know why, but anyway. But you can judge from the railings. These are normal waist height railings. What the scale. So the person is standing is about that high. So these are enormous constructions. They're about the size of a house. Some of these big ones. So if you get that burnt out, then I mean they're expensive and it's not easy to ship around and things like that. So anyway, they had problems with that. So they opened up the transformer, and that's what the windings look like inside. They'd overheated, and so that transformer had to be replaced. Right, I mentioned. You running out of power here? That's very fitting, isn't it? Actually, someone check the magnetic activity quickly. See what's going on. Can I just say okay? Okay, there we go. We'll wait until see what happens. They just got them come unplugged.
No, that's
No, it's not. No, he's there. Yeah. I'll keep going while it's there. The other system that can get affected is oil and gas pipelines. This is a picture of the Alaska pipeline. It's one of the most photographed pipelines in the world, I think. because most of them are underground, so you don't see them. So this is, you get lots of nice pictures with that. These were some recordings taken on the pipeline. And you can see you're getting current fluctuations up to 100 amps flowing along the pipe. So you're getting significant currents there. Anyway, well, and the concern there is that these currents, where they flow to ground, can cause corrosion of the pipe. The concern is actually the voltage on the pipe. And they do because the corrosion is an electrochemical process at the steel to soil interface. So by setting the voltage of the pipe with about 1 volt negative with respect to the surrounding soil, you can effectively turn off those corrosion processes. So here's some recordings of voltage on the pipe, and they've got it about 1 volt, and you see this is they want to keep it within this safe region. We can see during this magnetic storm, you get some voltage fluctuations going outside. Now those on their own won't cause any problem. The concern is more that perhaps over 30 years of magnetic storms, the cumulative effect of that might cause problems on the pipe. And that sounds a long time, but when the projected lifetime of these pipelines is about 60 years and they cost enormous amounts of money, then if it only lasts 30 years, that's a major economic loss. But in fact, there was one incident where we didn't even have to wait 30 years. 3 years after this pipe had been installed, they were detecting from various checks they do that there were problems, and they dug it up, and this was a corrosion pit that had already started on that pipe. Right, so the key thing now that I'm going to spend most of the time talking about is how magnetic disturbances affect power systems. But the first off, I thought I'd quiz you a little bit. Basic question. Why do power systems use transformers in the first place? Why not connect straight from the generation through to the plug-in? Why not generate at 115 volts and then just pipe it through, and then you could just plug in and save all this mucking about with transformers? Anyway. First year physics. Yes?
Has a lot of loss through resistance.
Has what?
Current.
Yeah, the current, the loss is because of the current. So how do transformers help that? Right, so by putting up to a higher voltage, for the same amount of power, you reduce the current flow, and then the losses is the I squared R from going through the transmission line. So if you can reduce the I, then you've reduced the losses. Yeah. So there's your normal transformer. You have your input winding and your output winding, or other way around. Something, if you're ever looking at this, you might come across is on the power system, they often combine these two windings. It's a bit of a trick, but it sort of saves, because those things are so big, it saves you having a second set of windings. You get the same effect by having just one winding, and you just tap off from the middle to give you your low voltage. You don't have to have a separate one. And these are referred to as auto transformers. One other thing that comes up is quite significant in this. One of the problems we get in this is a greatly increased need for what's called a reactive power. So I thought I'd better just explain briefly what is the difference between reactive power and real power. Now, real power is what you get when you plug in the wall. It's something that can really do work on your systems. So you've got your voltage that you're generating, you might have transformers in the way, but the load that goes out to the consumer is a resistive load typically. So the current that's flowing through here will be in phase with the voltage. And so that's called real power. You need a small amount of electric current, that's the magnetizing current, that actually operates the transformer. It's not very much. In fact, transformers are about 99% efficient. So you only need a little bit of power to operate it. But the key thing with this is an inductive load, so the current here is out of phase with the voltage. And so the power that's used is referred to as reactive power, And so the key thing about that is that's where you've got the voltage and the current out of phase. And so your normal thing for real power is the voltage times the load current, and then the reactive power, this is volts times amps, and R for reactive is where that VAR term comes from, is the voltage times the magnetizing current. Now, the other bit of basic electrical engineering you need to know for this is that the systems use three-phase. Who's heard about three-phase AC? Good, two. Of the mature students at the back, yeah. Yes. This, yes, I mean, just by knowing about this, you can get a lot of insights, because sometimes in your street, you can find, if there's problems, there might be a blackout or something, you can have every third house is out. And you wonder, well, why, I'm out, but why my neighbor's got power? Well, every third house is on one phase, and that's what's had a problem, and the other houses are on the other two phases. So, but it's more efficient to generate with three-phase and to transmit power. Anyway, the key, and if you're driving around and you see these power lines, if you look carefully, you can see the lines are always in threes. So here this one, that'll be one phase, that'll be the other, and that'll be the third phase. So these big lines there's often a little line across the top of the towers. That's just to, in case of lightning strikes, to take that current to ground. That's not carrying in any power. Here's another one, different construction of the towers, but you can see here's the main insulators hanging down, so a line hanging on that one. There's one phase, second phase, and third phase there. So once you start to recognize that, you'll see that on all the power lines that you go under. The key thing for the geomagnetic effects, why I'm sort of laboring this a little bit, is because the three phases on the high voltage, on the very high voltage lines, are connected in what's called a star configuration. So there's the three phases coming in, and these three phases add up to 0. So you get the currents come in, and you can have the transformer, so power goes out on those lower voltage lines. But the currents add to 0 at this neutral point, and the same on there. And so, in principle, if everything worked perfectly, you could just leave it there hanging in the air. In practice, they connect this to ground, because there's two things can happen. One, you can get a lightning strike on one of the wires, so they want a path to conduct that current away to ground. And the other thing is, if one of the phases goes out, because there's a break in the line or something, then suddenly the three phases don't add up to 0 here. You've got an enormous amount of current coming into that neutral point, and you've got to dump that somewhere. So that's, normally there's no current flowing in there, but that's maintained as a key safety feature of the power system. Yep. Well, that is where one of the stability issues comes in with the power system. Is they're normally very careful about setting up the load on the three different phases to be all very equal. That's why down a street they do every third house. So averaged over the whole network, they'll be fairly even. What becomes a problem is if you've got very large industrial users, and if they were all on one phase only, like a car plant or something, then you'd run. But that's why they themselves go to three phase, and all their machines are operating on three phase. So, but yeah, that is an issue. And so, yeah, if you had a problem, and I mean, like if one of the lines goes out, then suddenly those consumers have lost power, and you have got the situation where the three don't add up to, and that's a problem. That's why they have to have this connection. Now, this is very significant because this influences the path that the GIC, geomagnetically induced currents, can take. So the currents can go along the lines and flow to ground or to and from ground through the transformers at the substations. And so you get a current flowing in at one substation, along the lines and out at the other substation. And we'll get into more detail about exactly where it flows later on. But that's the basic principle of the AC system and the features that affect the geomagnetic induction. Right, so now I'm going to get onto more specifics about all of the space weather side of things, about how you get the problems on the power system. So here's the chain of events. You start off with some magnetic field variations, and we'll look at the different characteristics, different types of variations. And then they produce electric fields at the surface of the Earth. And we'll show that the conductivity of the structure of the Earth affects that. And then you're getting more into the details of the power system that determines the geomagnetically induced currents. And then I'll show you about how the transformer response leads to various effects on the system. So these are all things that you should be familiar with, but I'm going to point out specific features because this is often overlooked. So just want to sort of run through quickly the typical features, the sort of standard terminology for a magnetic storm. You start off with a storm-sun commencement that can be a very rapid change in the magnetic field. And then the main phase, which is often characterized using the DST index, is quite a slow variation, decrease, and then a recovery phase. Now, there's often a lot of stuff superimposed on top of that, but as we'll see, that's more attributable to substorms. Here, I'm wanting to isolate this as the classic sort of main phase slow variation. And then up at higher latitudes, you get electric currents flowing around the auroral zone. This is an actual satellite photo, and then I've superimposed on where the electric current flows, so the auroral electrojet. And this can be up to millions of amps during a large disturbance. And you're getting magnetic substorms that last anything from sort of half an hour to an hour. So larger variation there. And then the other type of magnetic activity we see on the ground is our pulsations lasting anywhere from seconds up to minutes. We tend to be, in the GIC context, only concerned about the larger ones, the longer period, large pulsations like these examples shown here. So I'm going to now look at geomagnetic induction into an electric power system. The way we think of it physically is, you've got the auroral electrojet, that creates a magnetic field, varying magnetic field, that then is electromagnetically coupled into the transmission lines that gives you induction and induced electric field in the transmission lines. So the electrojet is east-west. The magnetic field around it is going to give you a north-south variation on the ground. Then that north-south changing magnetic field will give you an east-west electric field in the power system, in very simplified terms. In a real disturbance, the electrojet is much more distorted, or you can get other disturbances coming in, and your electric fields can go in a variety of directions. But first approximation, we often think of it as an east-west. My graphics didn't turn out. There's often a lot of confusion about the actual process of induction into a power system. And what I'm trying to show here is the green is the Earth. If this is a substation here, power line along here, and substation coming down here, so your circuit is like that. The great temptation is to use Faraday's law and say, okay, the electric field around that loop is due to the changing flux through that loop. But if you do a back of the envelope calculation, and this is one we should have had going, you find that the magnetic field change through that is insignificant. So effectively zero, even during a big storm. It's not adding up over the area. It's not very much at all. So you say, okay, there's zero induction in there, so the electric field around that loop is zero. So then some people make the leap, well, say there's no induction into that system. but I want to show you how they're wrong about thinking about that. It doesn't mean that there's no electric field. It means you've got to be careful about literally what you're saying. There's no electric field. The sum of the electric field around that loop adds up to 0. But you can achieve that in 2 ways. One, by having no electric field there at all. The other way, by having an electric field in the line, that's that way, and an electric field in the ground, that's that way. That's the same. So really what this is saying is that the electric field in the transmission line is the same as the electric field at the Earth's surface. Does that make sense to people? A few heads nodding. Okay. So we in fact use this, and then we do all our calculations for the electric field at the Earth's surface, and then apply that to the transmission line. So that's what I'm going to jump onto next. It was very interesting, some of the discussions earlier, and the way some of the things were described, I thought, well, that applies to this situation as well. And one of the plasma physics descriptions was about, well, you can't just say, well, this causes this, because you've got almost a feedback effect. You get a self-consistent solution. Well, it's very much the same with this. There's, again, a lot of confusion. A lot of people say, well, E is proportional to the rate of change of the magnetic field. And that, in fact, is not the case. What happens, you get the magnetic disturbance. That drives electric currents in the Earth. Those electric currents themselves create a magnetic field, and that adds to the external source field and contributes to the field that you observe at the Earth's surface. Now, the effect of the induced currents is it's acting in a way that it tends to cancel the external field. So as you go deeper into the Earth, then that cancelling effect means that the magnetic field falls off and the currents fall off. So you get a skin depth effect. And with high frequency variations or with high conductivity areas, the skin depth is very shallow. I mean, this applies across all ranges, like radio frequency problems see this, AC induction sees this, but there you're talking about the skin depths might be only meters. Here we're talking about kilometers into the Earth, and when you get into the lower frequency magnetic field variations, like periods of an hour, say, and in a low conductivity region, then the magnetic disturbance can go hundreds of kilometers into the Earth. Now this is significant for us because it means that to really, the field goes 100 kilometers into the Earth, but in turn, the conductivity down to those depths influences what we see at the Earth's surface. So it means that we've got to know something about the electrical conductivity deep within the Earth. So this is a review of basically what the Earth's structure is: solid core, liquid outer core. When you get up into the mantle, that's a fairly good conductor, and when you get nearer the surface, the crust is a fairly high resistance material. And then a lot of variability with all of the either sedimentary rocks or the igneous rocks at the Earth's surface. A lot of it depends on what the water content is in the rocks as to what their conductivity is. Sedimentary rocks have a lot more water content, so that they're more conductive. And here's a table of range of resistivity values for all the different types of rocks. So, so what we do with this information, first of all, you look at it and think, good God, what can we do with it? Then you hire a geologist who understands all this stuff, and you get him to come up with a whole bunch of Earth models, which is what we've done for all the different regions. The basic structure here, we've got the Canadian shield that's the heart of the continent, so some of the oldest rocks on the Earth. So that's very high resistance. You've got a lot of, all through the prairies, you've got a lot of layers of sedimentary rocks, and you've got the mountain belts on either side of the continent that distort things. So from that, all that geological information and various sounding techniques, you can build up profiles of those. So these are some samples of these. And then there's modeling techniques, and we basically have a recurrence where if you work through the maths, you can work out what the impedance is looking at the surface of this lowest layer here, get the Zn. Then that you can factor in and do the calculations for the next layer up, where you can calculate what the impedance at the surface of that is based on the reflection coefficient at this lower edge, which factors in the lower one. So then once you know that one, you can do the same for the next layer and so on up to the surface. So from that, we can calculate a surface impedance. And now, in going through all that, as I said, the skin depths are different vary as a function of frequency. So you repeat those calculations for the layered earth for all the different frequencies across the range that you want. So you can come up with the surface impedance Z as a function of frequency. And so with that, you can easily relate the magnetic field variations, use that with the Z at any particular frequency to calculate the electric field. So that's at the heart of what we're doing. But then in practice, when we've got a time series of information, we start off with the magnetic field. We do a fast Fourier transform of our time series to put that in the frequency domain, do these frequency domain calculations to get the electric field spectra, and then do an inverse Fourier transform to get a time series of electric field values. So this effectively is treating the Earth response like a filter. And in fact, the Earth looks very much like a high-pass filter. It tends to accentuate the higher frequencies. So this is an example of the magnetic field spectra, the Earth response, changing with frequency and the phase changing. And then this is the electric field spectra that we get out from that. And then after doing these calculations, this is, that was the magnetic field data that went in, and these are the electric fields that we get out. So the Bx is the northwards component of the magnetic field. So we use that to calculate the eastward component of the electric field, that one, and then the eastward magnetic we use to get the northward component of the electric. So the fields are orthogonal. And you might recognize this is a famous date. This is the March '89 storm. And in fact, it's that substorm, that rapid change there that killed Hydro-Quebec. And you can see the large electric field that generated. And that was what caused the problem. Yeah. So from that, we can work out what the electric fields are that the power system is going to experience. So the next thing we want to do is to model, well, so what is the geomagnetically induced currents that are going to flow in the power system. So we've got our basic three-phase network here, and having gone to all that trouble explaining about three-phase to you, I'm now going to say the first thing we do is we do a one-phase equivalent for that, because what we're assuming is that each phase is going to be affected exactly the same. So to save work, we just do one phase. And the key things we're looking at are the resistances of the lines, the resistance of the transformers, and the resistances going to ground here. All right. And so here we are. So we can basically set this up. This is to illustrate this as a series of loops here, and we can produce equations for each loop in terms of the voltage induced in each line. And so just using, this is kind of first year physics, Kirchhoff's law, circuit analysis is all you need. This is an equation for the four loops. You've got the four equations. You can collect the terms in terms of the currents, and gathering terms. And then you've got four simultaneous equations that you can solve, where in practice you can set that up as a matrix equation. And especially you need to do this when you're doing this for a whole network with kind of hundreds of loops there. So you've got a matrix equation relating the network impedances and the currents that you're trying to find and the electric fields that you're applying, and then you just do a matrix inversion. So you can get out an expression for all of the geomagnetically induced currents in every branch in the system as a function of the system impedances and the electric fields that you're applying. Now, Now, okay, so we've got the modeling techniques, but it's useful to get some insight into the factors that affect the results you get. And this is one of the things that, as you go to a longer line, then the voltage you're applying in the system is the integral of the electric field along the length of the line. So the longer the line, the larger the voltage. So some people have run with that idea and said, okay, the longer the line, the bigger the GIC. Well, that's true up to a point. Looking at this very simple circuit, there's the total resistance in there. You'll see the resistance of the line is one factor. There's the equation for that. When we actually do this, you find that you approach a limiting value. What's happening here is that as the line length increases, then the resistance of the line becomes much larger than the resistance of the substations. So you can drop off that last term there. Then you've got E times L over R times L. The L's cancel. You just get E over R. So you approach a limiting value that's the maximum GIC that you could get in that type of line. Now, something else from a practical point of view, higher voltage lines tend to have larger GIC. And the reason for this is that as you go to higher voltage, you've got more of a problem with having electrical discharges into the air with arcing from the lines. And you can reduce the arcing by having a much larger conductor, because then the angle of the curvature, the radius of curvature, is greater. And so you've got less like how you get a discharge from a point. Well, if you can round it off, you get less discharge. But if you just made the conductors bigger, they'd be far too heavy. They found there's a trick they can do with that. If you have 4 conductors on spacing, it gives you the same effect as if you've got a very large conductor. So as you go to higher voltages, first they go to, these are typically single conductors, these are typically double, and then by the time you get up to these voltages, these are 4 conductor bundles, and sometimes even going up to 6 conductor bundles. And so you've got more conductors there, so it's a lower resistance path, and so you get larger GIC flowing in those circuits. Something else. Now, right, this is a good exercise. Which sites, this is our simple line, substations A, B, C, D, and E. From looking at that, can anybody tell me which substations are going to see the largest GIC? Right, good. Yeah. If you just look at these loops, you've got a current flowing down here is tending to cancel the current flowing up here, and vice versa. So in the intervening stations, the loop currents tend to cancel. The only place that's not happening is at the ends of the network. So you tend to get the effect the GIC flows in from one edge of the network across the system and out on the other edge. And so you don't tend to get as much GIC in the middle of the network. So when you have problems on the system, it's not as if every substation is affected. There are specific, very basic ideas that you can understand why different parts in the network are affected. So we've identified, so we can calculate the electric fields, we can put that into a power system model and calculate the currents. We've got an idea where the currents are going to go. So they're going to flow to ground at the transformers at those substations. So now the key thing is this is what happens in the transformers. And this is a little bit unusual when you're not used to it. Perhaps I can just draw on here. If I asked you to draw a hysteresis curve, well, perhaps I should. Who can draw me a hysteresis curve for a transformer? Everyone ducking. And does that look familiar? Yeah. So, this is the normal hysteresis curve if you're applying a magnetic field to a material. What we've got there is very much a variation of this. The area inside this curve represents losses inside the transformer. So there's a lot of engineering design goes into reducing that. So what they've really done is they've taken that curve, but then, and it's, so it's very thin there and sharpened off the edges. So here's the normal operating region. And then if the transformer saturates, you're taking it around this knee and you're up in this. This represents the saturation region of the transformer. So in normal operation, it's working symmetrically and you have a sinusoidal voltage applied, you get a sinusoidal electric current associated with that. When you've got GIC in there, it's creating extra magnetic field inside the transformer, and that's offsetting the operating point of the transformer. So it shifted it up away from the central region, and now the voltage is going around into the saturation region. And just by doing some so if you just trace each point on the voltage curve across to the curve and down here, you can construct the waveform for the current. And you can see every half cycle like this, you get a large spike in the current. And that's one of the main problems that's due to GIC. Now, analyzed in terms of its frequency content, that means you've got a lot of harmonics in the system. And so, yeah, so you've got the spiky waveform gives you a lot of harmonics. Now, a lot of relays to protect the system are designed to detect harmonics. So suddenly having all these spurious harmonics around causes misoperation of those relays. The other thing, and if you remember back to when I was talking about reactive power and the magnetizing current gave you reactive power, the transformer is not operating as efficiently, so it's drawing more magnetizing current, so more reactive power. And if you don't have enough reactive power on the system, then that's when you can get voltage collapse. And here's an example, recordings of reactive power fluctuations during a magnetic storm. The other thing that's happening when you're getting saturation of the transformers, what does saturation actually mean? It means that the metal core of the transformer can't take any more magnetic flux. So the flux is going to spill out into the surroundings, so into the windings or into the frame of the transformer. And so there it can create eddy currents in those locations that can create localized heating. And heating has been a big concern for transformers, but it's not the overall temperature of the transformer as a whole, it is just very localized. So here's an example. The blue is the geomagnetically induced current. So you can see it goes up to a peak here. These transformers are immersed in oil to dissipate all of the heating in normal operation. So by measuring the temperature of the oil, you can get indication of what the average transformer temperature is. So that's the green. So that's that one here. So you can see that doesn't change hardly at all. But in this transformer, they did some measurements on the tank outside, and that's this. And you can see a big spike in the temperature associated with this GIC. And we're going up to 170 degrees centigrade. So that's a big concern. And it was this kind of very localized heating was what caused the problem in that picture with the burnt out transformer that I showed earlier. So I just want to recap what we've been talking about now. We've got the magnetic field variations, comes through induction in the earth, into the power system, and into the transformers. Now, I mentioned the different types of magnetic variations for a reason, is that they've all got a different frequency content. You've got the main phase of the magnetic storm is fairly slow variation. You've got the substorms a bit faster, you've got pulsations, and then you've got the SSC. And because of the Earth response, that's going to accentuate the higher frequency fluctuations, going to give you larger electric fields. Now, up to now, we've been modeling the power grids as a resistive network, but the transformers themselves have got inductance. And something that we need to look at is whether there's just the L over R time constants of those are going to limit the higher frequencies. And that's what I think is happening. And so, unfortunately, this year, the text has changed. It's a bit like the three bears story, but a variation. Who's been sleeping with my power system? It's that the main phase is too slow, the SSC are too fast, but the substorms and the pulsations are just right in terms of the frequencies to cause problems. So now I want to throw out to you what new knowledge we need in this area, and it can really be broken into three types of things. Defining the 100-year disturbance, are there theoretical upper limits we can put on the disturbances, and improving predictions. Now, we've got records going back 150 years, unfortunately rather incomplete, and the systems have evolved considerably over that time. A general feature that we're finding with all the modern systems is there's increasing vulnerability. And this is creating a much greater heightened awareness of these problems due to space weather. And one of the key things that they're concerned about is, well, sort of, what should we design for? And it's like a bridge builder. They design for the 100-year flood. Well, now the power engineers are asking us, well, what's the 100-year magnetic storm that we should design to? And so we're looking back at historic record of some of the really major disturbances. So there's the 1859 storm. There's the 1921 storm when the telegraph station in Sweden burnt down. It was another big one. And then the 1989 with the Hydro-Quebec blackout. And so we're trying to build, and with other data, build up a decent statistical record to try to estimate those. Another key question that was asked that really throws this back into your court is there an, never mind 100 years, because I mean, it's almost, if you do the statistics, you can extrapolate off your curve, you can get almost any size of disturbance that you want if you wait long enough. Now, the group that we're also associated with is doing a lot of the earthquake monitoring in Canada, and they have the same sort of issue. How big an earthquake can you get? And they often do statistics showing sort of, you get a lot of small ones and then a fair number of medium ones and then a very few large ones. A typical trend down. And I was sitting in on a talk about this, and someone presented this, and he had a curve going down, but then he actually curved it down at the end. And I jumped him and said, is that just because you're running out of data, or is it? And he said, no, they have reasons to think that in specific areas, there's an upper limit on what size an earthquake could be, and it's based on the length of the fault and the strength of the rock, so how much strain you can build up before it's going to give. So that started us thinking, can we do the same sort of things for space weather events? And I was very interested in some of the talks earlier were alluding to this, or looking at I think it was Dr. Shriver's talk about the evolution of our sun as a star, and that we might have had larger eruptions earlier on in its lifetime, but now it's come down to a certain level of activity where we could only expect a certain size of eruption. So, I mean, are there things from basic physics knowledge that we know, that we can say? I mean, is there a maximum size to a solar flare? I mean, that's not necessarily the trigger for our GIC problems, but as an indicator, or a maximum size of a CME. And this is, I'm hoping we'll get some people throwing in some discussions later. Another one that people are very concerned about, the speed of the CME. And the 1859 event was a very fast one, but we found with some other ones that speed is not necessarily everything. Like there was August 1972 was a very fast event, but we didn't see that large a disturbance on the Earth. And then is there a limit once the CME hits the Earth, all of the interaction with the magnetosphere, are there physical limits on how much energy can be stored in the tail before it gets dumped in and gives you a substorm? So are there limits on the actual size that you can get for a substorm? And here we want to focus on the specific disturbances, not necessarily the DST, reflecting the main phase. There's been a lot of focus on the 1859 showing, well, that's the biggest storm. Well, that part of the disturbance doesn't cause the problems to power systems. And just having a large DST is not a good proxy for substorm size. So we need to be a bit more focused about what type of disturbance we're talking about. A key thing in terms of risk to specific power systems is how much of an expansion. During large disturbances, the aurora zone expands. So how far does it expand? Is it going to come down over the US and cause problems? And so what exactly are the solar wind conditions that will lead to that expansion of the aurora zone? That's a key factor that we don't really know. And that's where a lot of kind of space weather, space physics knowledge can feed into very practical problems. And then the size of the substorm, we get a buildup of energy in the tail. Why does, in some cases, it keep building up and then release, or in some cases it builds up a little bit and then releases before it's got too big? I mean, what are the factors controlling that? We did an investigation of the March '89 storm that caused the Hydro-Quebec blackout. And in fact, it looks like there was 2 CMEs that hit, not just one. The first, and in fact there were 2 flares in the right sort of time interval a couple of days before the storm. And there was a storm sun commencement about 6 hours before the Hydro-Quebec blackout. And then a couple of years after the event, I saw some reports that a second storm sun commencement had been identified. People had looked at some low latitude records. There was too much going on in the high latitude. But from some lower latitude records, they had identified a second storm sun commencement. And that was exactly at the time of the Hydro-Quebec blackout. So was there a particular set of circumstances where the first CME was interacting with the magnetosphere, you're getting a build-up of energy in the tail ready for a substorm, and just at that time, the second CME hit and perhaps shook loose a lot more energy than might have been dumped otherwise and gave a much larger substorm. So that might be part of the scenario of why we had such problems during that particular event. And then, of course, we want to use all this knowledge to improve predictions, whether, as they're saying here, we're using the crystal ball mumbo jumbo or statistical probability. And the kind of things, again, the similar sort of things, CME speed, not necessarily as an indicator of the size of the disturbance, but just it'd be nice to know when it's going to arrive so we can tell the power companies that. The big thing, of course, that we're still missing is knowing what the IMF orientation is in the CME. That's really the holy grail. If we can find a way to detect that before it gets to ACE sometime out, that will be big. And then the size of the substorms and be able to predict how much the aurora over is going to expand will be a key thing for us. So as the last part, I just want to mention about assessing the geomagnetic risk to power systems, some of the work that's going on. There's been a geomagnetic disturbance task force set up by the North American electric power industry. So this is very much a hot topic at the moment. And they're doing a lot of work looking at the vulnerability of transformers and things like that. But they're the ones who push for this kind of definition of this 100-year magnetic storm or a theoretical upper limit. But the practical kind of thing we can do, we can use the modeling skills I've been describing to model specific power systems. So this is a model of the Hydro-Quebec electric power system and with a northwards electric field. And you can see here the current's flowing in at the southern end, up the transmission lines and out at the north. And so these are the GIC in the substation, so we're seeing the largest GIC at some of these sites at the edges of the network. And we can do the same for east-west electric field, and here the flows are different, more coming in and going across the network here. So this, we think, is a more realistic scenario for what happened in March 1989. And then you can change your directions of electric field, and you can see how the amplitude of the GIC at different substorms changes with the direction. So here we've got the size of the electric field constant, but we've just changed the direction. And you'll see this one, LG2, the Grand Chief, if I just go back, that's this one up on here. So lines going in that direction. So you can see that the maximum GIC is when the electric field is aligned with the transmission lines going into that site. And the same with the others. So, right. So the conclusions I'd like you to take away is that space weather is a natural hazard of the technological age. It's one of the harder ones to explain to people because people can feel earthquakes and they can see floods. They can't see a magnetic storm. And in many systems, there's increasing vulnerability. It's been quite fascinating to look at for completely different reasons on satellites, on power systems, pipelines, whole other range. But the general trend is increasing vulnerability. So there's becoming greater awareness of these issues. And so hazard assessment is needed to determine the extent of the problem in the first place, and then understanding of these space weather effects can really assist in the design of engineering solutions. So any new knowledge you can generate, there's a market out there waiting for it. And then we need to improve the space weather forecast, and if we can do that, then sometimes there aren't good engineering solutions, but there might be operating procedures that can be implemented to see the system through, see the power system through. They're even at these Geomagnetic task force meetings been talking about the unthinkable, or what would have been unthinkable in the power industry some years ago. Faced with the scenario where if you had a really big magnetic storm, it's been suggested you might have hundreds of transformers burnt out, and it could take years to get all those built and reinstalled. That instead of having a power system or parts of a power system down for months or years afterwards, it might be better to actually switch off the power for a day if there was a big enough magnetic storm. Now, no one's quite ready to do that at the moment, but the fact they're even willing to consider it is a big step forward. Because what's really going to be needed is accurate enough forecast. If someone does that and it's a false alarm, then there's going to be hell to pay. So they're not quite ready for that. So anyway, okay, thank you. Yes, that's interesting. That basically I've focused on the CMEs that cause the magnetic storms with the main phase, but the point was made that a lot of the oscillations in the field you get with the high-speed streams associated with the coronal holes and the co-rotating interaction regions. Yes, that's exactly right. We're especially conscious of that up in Canada because we see quite a lot of activity from high-speed streams. And we've got a plot on our website that shows all of our magnetic observatories ordered in terms of latitude. So you can very easily see where the activity is. And our risk factor I was talking about expansion of the auroral zone, you see, from our experience, we seem to only get that expansion when we get a CME or a classic magnetic storm. When we've got high-speed streams, we see often very high activity, but up at higher latitudes. And it tends to stay at those higher latitudes. So it can be a risk for some of the northern Canadian power systems. but we never seem to see it move further south. That's one where I've got myself into trouble. I used to say yes to that question. That's a very idealized picture of the electrojet and the disturbances. From our records, it looks like that's a fairly good description of the March '89 storm, of the particular incident that caused the Hydro-Quebec problems. But certainly, we need to be careful not to overstate that during disturbed times, it's a much more irregular up and down. You can get electric fields all over the place. Yeah. Yes. Yes, the suggestion was that if the main disturbance is an east-west electrojet, it's giving you electric fields that are east-west, so it's affecting those lines and not the ones that are north-south. And if I can just go back. And in fact, this was something that I still think that there's confusion about the Hydro-Quebec system, because their main lines are north-south, and that's where the power flow is. The AC power flow is coming down from generation up here, down here. Down. So they tend to think of that as mainly a north-south connected system, and almost sort of don't take so much notice of these interconnecting lines in the middle. But in fact, we think that during the March '89 storm, it was indeed the east-west flow across the system that was causing problems. And there's some things to support that in that, if you remember back to the original one where I described the blackout, the places where they were having the things tripping out originally were at these substations here. So that seems to fit with that scenario. Yes, well, we're doing some work at the moment with Hydro-Quebec where we've set up a model, we've redone this model, and the engineer that we're working with has gone back through on the system logs to identify that there were a couple of lines were out of service at the time, so we've pinned down to and got a model of the system as exactly as it was on the night of March the 13th, as far as we can tell. And so we're modeling the GIC in that, and then what we're going to do is set up a model for the system as it is now. And what they've done to improve the AC flow is they put a bigger capacitors in these lines. But that has the added effect that it blocks the GIC. But it's only in the north-south lines. It's not in these little interconnecting lines. So we're going to be examining just how much GIC flows in these and how much of an effect there is on the system. Because Hydro-Quebec is still seeing harmonics on their system during magnetic storms. And if it was all just north-south, you wouldn't see anything. So there's still some GIC flowing somewhere, and we're going to try and pin down exactly where it's going.
How sensitive is this to your underlying model of what the conductivity is, what your kind of conductance profile within the Earth?
In the Earth, yeah. Right, the question was, how sensitive is this to the Earth conductivity structure? And yes, it is quite sensitive to that. And that's one of the contributing factors for our Hydro-Quebec, because it's on a very resistive Earth layer there. So you're getting larger electric fields as a result of that. And so that's one of the factors has to be taken into account.
So
Yep.
maybe a follow-up. So that conductivity is dependent, in part you said, like on the water content, which I guess is, so this could be stronger during the wet period than the drought.
No. No. That, what you're describing, does affect things like radio propagation and that, where the skin depth is only in the first meter or two, where rainfall and that will affect things. This, we're looking so much deeper into the Earth that very surface effects are insignificant in the scheme of things. Yeah. Now that's one I left out to simplify the problem. What I've looked at here is assuming the Earth is just horizontally stratified, and look at just at that at the variation with depth. Now, when you get, if you've got a conductivity boundary, and the classic one is between the land and the ocean, you get large induced currents in the sea, come in here, and you've got smaller induced currents flowing in the land because of higher resistance in the land. So you get a charge build-up on the coast that then, overall, you've got to look at a self-consistent solution that takes into account all of this. So this acts to deflect the currents deeper down and reduce it. But the one of the effects of this is it increases the electric field on the land side of the coast. Now that's something where we're wanting to do more modeling on, because we want to see, well, exactly how far in from the coast does that extend? Is that significant? Is it 1 kilometer? Is it 10 kilometers? And how much it would affect this. And then one of the other subtleties when you really get into this is, well, what is the boundary you should use? Because at the coast that we see, it might be a boundary between the land and a very shallow sea that's on the continental shelf. And in fact, the more significant boundary is actually the continental margin, where you're going down to deep ocean water, kilometers deep compared to 100 meters here. So there's probably a double effect, one from that. And then it'll be different frequency ranges, because it's the longer periods we go deeper into the ocean. They'll see that continental boundary as the dividing line, whereas the higher frequencies are more affected by the shallow sea, so they'll see the actual coastline as the boundary.
Has there been any evidence of a significant GIC effect from isolated substorm, ones that aren't directly part of it?
Not that I know of, and I think, because my experience has been that, okay, you get them, but they tend to be smaller. So it's really the biggest substorms that cause the problems are only occurring during a major event, like the 89 event. But we can very closely tie it to an actual substorm. It's not the main phase doing anything, it's the actual substorm.
A few years ago, the House of Representatives passed legislation known as the GRID Act that would require the system operator of builders of transformers to install blackout devices.
Yes.
What's your view on
That we'll let the students answer after the lab period, because that's one of the things they're going to test, is what happens when you block the GIC from flowing to ground at a particular substation. So we'll wait for them to come up with the answer to that.
Actually, what are the time scales that are involved once during the course of the storm? Such a huge event.
Well,
Like whether it's instantaneously transfer.
oh yes. Oh, sorry, yes. What are the time scales of the event? So you mean for the outage in the power system? Yes. From the sequence on the Hydro-Quebec, from the time that the first SVC tripped out, static var compensated. Now that you've gone through and understand the sequence, I can skip back to that. Then I can walk you through that event, and you'll understand it a lot more now. Right, okay, so the electric jet came down, and this is about a surge of current of about 2 million amps. So the previous minute there wasn't very much, and then that, in about a minute there was a very rapid jump. And this gave us a magnetic field variation of about 2,000 nanoteslas over a couple of minutes. And then now I've explained about the harmonics and I've explained about reactive power. Now, to maintain enough reactive power on the system, one of the things they do is they put static Vara compensators, SVCs. That's what they're there. So there's a number of these on the power system. So they provide reactive power and help to maintain the stability of the network. Now, the transformers were saturating because of the GIC. So the transformers needed more reactive power. So these were needed more than anything at this time. But the saturation was also causing a lot of harmonics. And the harmonics caused these to trip out. So just at the time when they were needed the most, they were being tripped out. So as I was saying about the current flow, we think GIC is flowing across here. It's these substations that are being affected. And right, so those all four tripped out. And then without that to maintain the stability of the network, then the voltage started to drop. And you started to get surges of power up and down the network. The network was starting to go, the load end was going out of phase with the generation end. So the power was swinging up and down like this. So then the system automatically detected those surges of power and caused these lines to trip out. And then as I said, that caused the damage up there. So the start from when the first SVC tripped until when the system blacked out was about 90 seconds from start to finish. So the operators didn't have time to respond. The automatic load shedding that they have on systems didn't respond quickly enough. And so it was 90 seconds from the beginning to the end. So. Yep. Well, the Earth tends to accentuate the higher frequencies. The Earth response is like that of a high-pass filter. So you get larger electric fields with the higher frequencies. So that's why we've tended to sort of not focus on the main phase of a magnetic storm. We think that's too slow. So we focus more on the substorms and on the pulsations. Now, a lot of that was influenced by the records we had. We had 1 minute data going back to '89. Now the standard for magnetic observatories, a lot of other sites, is 1 second data. So we're seeing the faster variations a lot more. But so if you just looked at that aspect, you'd think, well, the faster variations, the faster you go, then that's more of a problem. So that would include the storm sun commencements. But a whole area that we haven't looked at that needs to be looked at is we haven't looked at the inductance of the power system. And of course, you've got these enormous transformers there, so they've got significant inductance. For this, we've been just modeling it as a resistive network. So I'm thinking we need to, before we rush off to do a lot with faster sample data and look at higher frequency events, we need to look at what the actual response of the power system is. Because I think the power system is going to damp out the higher frequencies. Yep. Right, the question was focused on Canada. I was trying not to be too nationalistic. I was more on the Hydro-Quebec just because that's the event that's everyone aware of. But there's a lot of concern in the US. The question was, what are factors influencing the risk in other countries, in other parts of the world? There's a big study going on in Europe. There's been effects seen in Scandinavia, like in Sweden. There was a blackout in Malmo in the Halloween storm of 2003. There's been a lot of recordings done in Finland. There's concern now about further south in Europe. There's a big study going on there. There's concern in China. I've got a PhD student from China who's working with me for a year. And a lot of interest over there because they might have not as large magnetic variations as we do in North America, but they go into much higher voltage electric power systems. So they've got an extensive 750 kV network, and they go into a 1,000,000 volt system soon. And so that's going to have lower resistance lines, so they're going to see larger GIC. So it's often, and then look at what the earth structure is in different parts of the country. And all of the countries around the world are going to have the same kind of range of conductivity structures I showed for North America. You've got in the kind of central regions of the continent, you've got the very old rocks that are the core of the continent. They're very high resistive. You'll have large sedimentary basins that'll be lower resistance, and you'll have mountain belts that'll be a funny combination of those. And so you need to look at all those factors in each specific location. And then the electrical systems is a factor, yes. Generally go into higher voltage systems because then they use lines that have lower resistance, tends to create larger GIC and put them more at risk, yes. Then there's been some transformers, the evidence seems to indicate some transformers burnt out in South Africa in the aftermath of some magnetic storms. And that was a surprise, and that's sort of still an area that we're investigating, because that's at a lower latitude than we expected to see a lot of problems. But we're trying to see how much it was a case of the system generally being stressed and those transformers being overloaded a lot of the time for normal operation. So it was more a case that the magnetic storm was the straw that broke the camel's back and that kind of thing. But so that could happen in other countries as well. Any other questions? Right?